If you're working with large language models today, you are definitely familiar with Retrieval Augmented Generation, RG. It's the superstar solution right now, right?
It absolutely is. It's the main paradigm we're all using to enhance LLMs, trying to patch up those big weaknesses like hallucination or, the fact their knowledge gets stale so fast.
RG is essential, I agree, but let's be honest. It's kind of a Frankenstein system.
It really is. I mean, you have these two totally separate modules. You've got a retriever that goes and fetches documents, and then you have the generator, the LLM itself, that has to write the answer.
And they don't talk to each other very well. That creates these massive bottlenecks, both in performance and just raw efficiency.
Exactly. And that's why today we're doing a deep dive into some really groundbreaking research that tackles this disconnect head on.
We are exploring CLaRa, that's continuous latent reasoning, a new framework from Apple and the University of Edinburgh. Our mission here is to unpack how CLaRa pulls off a truly unified RG architecture.
And it does that by solving two really fundamental intertwined problems that pretty much every current RAG system has.
Okay, so the first one is what the paper calls disjoint optimization. Basically, you can't train the whole system together, end to end.
Right. The retriever and the generator are trained separately, so the generator can't really tell the retriever, hey, that document you gave me was garbage.
And the second problem is this huge architectural mismatch. We use these tiny little vectors for search, but then we feed these giant bloated chunks of raw text to the generator. It just blows up the cost.
CLaRa promises a shortcut to fix all of this. It's all about document compression and joint optimization, all happening in one shared continuous space. The goal is to make RAG faster, leaner, and, well, smarter.
Okay, let's unpack this, the broken gradient problem first. Why is it such a critical issue that these two modules are optimized separately? What's the technical reason the learning process just breaks?
It really boils down to the nature of document selection itself. Retrieval is a discrete process.
Discrete meaning,
But
on or off.
Exactly. You're looking at maybe millions of documents, and your retriever has to make a hard binary choice for each one. Pick this, discard that. It's like flipping a switch. It's not a smooth, continuous decision.
And why does flipping a switch stop the learning?
Because for a neural network to learn, it needs a smooth path for error signals, we call them gradients, to flow backwards from the result. So if the generator gives a terrible answer, that error should go all the way back to the retriever and tell it, you picked a useless document.
But it can't.
It can't. That discrete selection, that switch flip, it's a wall. The gradient hits that wall and it just can't flow back efficiently.
So it's like the generator is screaming about the bad answer it just gave, but the retriever can only hear a muffled whisper.
That's a great way to put it. It ends up learning based on just superficial things like keyword matching, not on whether the document actually helped create a correct answer.
So the retriever stays short-sighted, only caring about surface-level similarity, because that really valuable learning signal from the generator gets blocked.
Precisely. That's the core optimization failure.
Okay, so let's pivot to that second challenge, the efficiency headache. This is where the real-world costs and latency really bite. You mentioned the architectural mismatch. What does that dual encoding process look like? Why is it so wasteful?
It's just redundant computation, pure and simple. So your dense retriever, it works by looking at these compressed vectors, these embeddings, in a database. That part's fast.
Right. Searching in a compressed space is efficient.
But the second it picks the top documents, everything reverses. The generator can't use those nice little compressed vectors. It needs the full, verbose, raw text of those documents shoved into its context window.
So the document gets encoded once by the retriever's model to make the vector, and then it gets encoded again by the LLM's own input layer to process the raw text.
That's it, exactly. And this just inflates the context window size like crazy. It's expensive, it adds latency, it drives up your operational costs. And, if you run out of space in the context window, the generator just starts ignoring documents, even if they're the most relevant ones.
So CLaRa's big idea, its main insight, is to solve both problems at once by encoding documents just one time into these super compact, what they call memory token representations.
Yes. These tokens have to be small enough for the generator to handle easily, but dense enough with information for the retriever to actually search against.
So how do they make sure that this intense compression doesn't just turn the document into, useless noise?
And that brings us to stage I of their process. engineering this high-quality compression using something they call SCP, or Salient Compressor Pre-training. This is where all the heavy lifting with the data happens.
Scaling compressor pre-training, so it's not just about making it smaller.
No, not at all. If you just try to compress a document by forcing a model to reconstruct the original text word for word, you waste all its capacity on, like, function words and trivial details. CLaRa doesn't want perfect reconstruction, it wants the semantic essence.
That makes perfect sense. We don't need a perfect copy of the text. We need a high-fidelity summary of the key facts and all the relationships between them. How did they train it to find just the salient information?
They used this really brilliant, novel-guided data synthesis process. They took a big LLM. In the paper, they used Qwen32B, run locally, to create a whole bunch of synthetic training data from Wikipedia documents.
And this data wasn't all the same, right? They had different types.
Right. They generated 3 complementary types, and each one was designed to push the compressor toward a different kind of goal.
Let's break those down. First one was simple QA pairs. That sounds pretty straightforward, like a basic fact check.
It is, but it's essential for getting the details right. Generating a question like, in which plant family is Trichocletis crinitis classified? It forces the compressor to hang on to those distinct atomic facts. It can't just smooth over important names or numbers.
Okay, and then the second type, complex QA. That obviously steps up the difficulty.
Oh yeah. Complex QA requires relational reasoning. It often forces the model to link 2 or 3 facts that aren't even next to each other in the original text.
So something like connecting a specific athlete, the year they were drafted, and the final score of a game they lost that season.
Exactly that kind of thing. This training pushes the compressor to capture the higher-level structure, the relationships between facts, which is absolutely crucial for any kind of multi-hop reasoning later on.
And the third one was just paraphrases. Why is simple paraphrasing so important here?
Because paraphrasing messes with the surface structure, it changes the words, the sentence complexity, but the core meaning has to stay identical. If the compressor can still find the answer, if fear the original phrasing has been all twisted around, it proves that the memory token it created is a truly abstract semantic representation.
It's not just a shorter version of the original words.
Exactly. It's a real test of linguistic compactness.
That is some seriously engineered pre-training. But even with all that great data, how do you technically guarantee that those little compressed memory tokens actually stay aligned with the full document's meaning? You need some kind of technical anchor to stop what the paper calls semantic drift.
And that technical anchor is a specific constraint they add during training, the mean squared error loss, or LMSE. This detail is really crucial. The model is constantly calculating the distance between its new compressed representation and the original uncompressed one in that high-dimensional embedding space.
Okay, so in simple terms, the MSE loss is basically telling the model, sure, you can squish this 1,000-word paragraph down into 60 memory tokens, but the final semantic address of those tokens in concept space has to be exactly where the original 1,000-word paragraph was.
That's a perfect analogy. It acts like a rubber band, constantly pulling the compressed vector back toward the source document's semantic home. Without it, the compressed vectors could just wander off into unrelated territory, and they'd be useless for both retrieval and generation. This whole process ensures StageI delivers really robust, high-fidelity compression.
Fantastic. So StageI gives us these short, dense, high-quality memory tokens for all of our documents. This sets the stage for the main event, Stage 2, the continuous latent reasoning loop, where retrieval and generation finally get unified.
Yes. So in Stage 2, that document compressor we just trained, it gets frozen. Its compact outputs are now our new document corpus. And then they introduce the query reasoner.
The query reasoner.
It's an adapter, initialized from the compressor's own weights, but this part is trained end-to-end with the generator.
And the whole point of the query reasoner is that it encodes my question, my query, into the exact same continuous space as those compressed documents.
Right. Which means you can now search memory tokens against query tokens directly. And because the query and the documents are now living in this shared, continuous, differentiable space, that discrete step, that hard choice of picking a document, it's no longer a brick wall for learning.
So we can finally use the gold standard loss, the next token prediction loss from the generator, to supervise the entire retrieval process.
It's a form of weak supervision, but yes.
Okay, wait, hold on. Even if they're in a shared space, you still have to select the top K documents to actually send to the generator, right? You still have to say yes, document A, and no, document B. Isn't that still fundamentally a discrete switch-flipping action that should break the gradient flow?
That is the core challenge, and CLaRa solves it with a really clever trick called differentiable top K selection, which is enabled by a straight-through estimator, or ST estimator.
A straight-through estimate.
Think of it like a very clever two-sided street sign.
Okay, I like that. Tell me more about this sign.
In the forward direction, when the model is actually running inference, answering your question, the sign reads discrete. The system does the hard binary selection. It grabs the absolute top K documents, just like a traditional retriever.
And then in the backward pass, during the learning phase.
In the backward direction, when the network is calculating its errors and updating its weights, the sign flips and it reads continuous. The ST estimator provides a soft, differentiable approximation of that top K ranking. It creates a smooth path for the gradients to flow all the way from the generator's final answer back to the query reasoner to update it.
Wow. That is the technical magic that ties the whole system together. That gradient coupling rewards the retriever, not for finding documents that just look like the question,
but for finding documents that actually maximize the likelihood of the correct downstream generation. It completely changes the retriever's objective from surface similarity to maximizing usefulness for reasoning.
and it's incredibly efficient. CLaRa doesn't need all this expensive human-labeled data. It just uses the language modeling loss itself, the simple ability to predict the correct next word, as a natural, scalable form of weak supervision for the entire process.
Exactly.
We have to talk about the proof then, because the results in the paper really confirm this unified approach works dramatically better. CLaRa is getting state-of-the-art results on really tough QA benchmarks, right? NQ, Hotpot QA, music.
And it's doing this while using a tiny fraction of the context. The efficiency figures are genuinely stunning. The paper mentions compression ratios up to 16 times smaller.
And it's not just performing as well as models that see the full uncompressed text. It's often beating them.
It often surpasses them, which feels totally counterintuitive.
It does. If you throw away 90% of the text, how can the model possibly be smarter?
Well, the theory is that this SCP compression isn't just lossy. It's an incredibly effective noise filter. By forcing the document into that tiny memory token footprint, the compressor is implicitly throwing out all the irrelevant context, the filler words, the repetitive junk.
Leaving the generator to focus only on the essential, reasoning-relevant facts.
Yeah.
Less noise equals better performance.
And faster inference. But the most convincing piece of evidence for me is the retrieval performance itself. CLaRa's retriever, trained only with that weak signal from the generator.
It actually outperforms fully supervised, purpose-built re-rankers.
It's phenomenal. I mean, look at Hotpot QA. That requires complex multi-hop reasoning. CLaRa got a recall at 5. That means it put a relevant document in the top 5 slots of 96.21%.
96%.
And that just blew past these highly tuned baselines like BGE re-ranker, which only got to about 86%. It proves that the generation loss is an extraordinarily powerful signal for teaching a retriever what genuine relevance for an answer actually looks like.
Okay, and here's where it gets really interesting for me. This is the part that confirms the query reasoner is actually reasoning, not just doing fancy pattern matching. The team used a technique called logit lens analysis to peek inside and see what concepts the query reasoner was encoding before the generator even saw the documents.
Right, they used that really tricky query from the paper. How many yards did the nephew of Ivory Lee Brown get during his 2004 true freshman season?
Which is a complex question because you first have to figure out who the nephew even is.
Exactly. The original question only gives you names and a date. But when they looked at the continuous embedding that the query reasoner produced, they found it had implicitly decoded tokens for concepts like NFL and Oklahoma.
Words that were not in the original question at all.
Not at all. That's the smoking gun. It confirmed that the joint optimization process actually caused the query reasoner to perform the first step of reasoning on its own. It connected the family relationship and the season to the likely facts before it even started searching.
It built a conceptual bridge for the generator to walk across. It made sure it retrieved documents specifically about Adrian Peterson's time at Oklahoma, not just general documents about Ivory Lee Brown.
This really proves that the name continuous latent reasoning is dead on. The reasoning isn't just happening in the final generation stage anymore, it's baked right into the retrieval mechanism itself.
So to sum it up, CLaRa is this huge leap forward. It unites this high-quality semantic compression from SCP with differentiable end-to-end training using that ST estimator trick. It creates a faster, more accurate RAG by just fundamentally solving that historical divide.
The end result is a system that creates these robust, dense, and incredibly compact semantic representations. And the research team notes this opens up some really fascinating avenues for what comes next.
Right. Today, these compressed tokens are used for efficient retrieval in RAG.
But given what we now know about their ability to capture abstract semantics, to capture reasoning relevant knowledge like connecting a player to their university implicitly, you have to ask, could these memory tokens serve as an efficient, actionable reasoning memory for future, much more complex agentic LLM frameworks?
And that's the provocative thought we want to leave you with. Perhaps this document compression that we built just for faster retrieval will actually become the core high-density memory system for the next generation of AI agents that need to plan and reason across many, many steps.